So today we're going to talk about logarithmic differentiation. So logarithmic differentiation, basically we just use logarithms and their properties to differentiate pretty complex functions. Usually these functions can be differentiated using different differentiation rules, but usually we use logarithms to make them a bit simpler, and sometimes they can't be, they have to be differentiated using logarithmic differentiation. So some functions that can be differentiated using logarithmic differentiation include exponential functions, complex rational functions, or other complex functions. So here are some properties of logarithms. The ones that we'll be focusing on are 5, 6, 7, and 8. So 5 being the log of a times c is equal to log of a plus log of c, as long as they have the same base. Similar thing with division, so log base b a divided by c is equal to log base b a minus log base b c. Number 7 is also pretty important, so if we have log base b a to the exponent c, that is equal to c times log base b a. And finally, just sort of a definition, log base e, where e is the natural exponent of anything, is ln. So ln, the natural logarithm, or ln. All right, so a procedure for logarithmic differentiation is, first we have to take the ln of both sides, so a natural logarithm of both sides, and use the properties of logarithms to simplify. I mean, I suppose you could take any logarithm with any base, but the natural logarithm works best, I find anyway. Then you want to differentiate both sides with respect to x. So this is the start of our implicit differentiation. Solve for y prime, or dy over dx, and then replace all instances of y in the derivative with what y was equal to in the original equation. This is so that the derivative doesn't have any instances of y left, and I'll show you in the upcoming example. So this is the example we're going to work through. So it's a pretty complex rational function, which you could technically solve using using the product rule and chain rule and whatnot, but it's fairly difficult. Then there's also one of these functions as well, just as an extra example. But let's work on this one. So we have y is equal to x plus 1 squared times 2x squared minus 3 all over square root of x squared plus 1. Okay, so what we want to do first is take the ln of both sides. So ln y is equal to the ln of all of this. So we can just rewrite it. And then we can use log laws to simplify the right side. So I'm just going to move this over a little bit. So say ln y equals to, so we have some multiplication and division happening. So we can say ln of x plus 1 squared plus ln of 2x squared minus 3 minus ln square root of x squared plus 1. And I'll just point out now that that is equal to x squared plus 1 to the 1 half, which we know just exponent laws. That'll just make it easier for us to simplify a bit more. So then what we're going to do is take some of those exponents out. So just simplifying further, ln y is equal to 2 ln x plus 1 plus ln 2x squared minus 3 minus 1 half ln x squared plus 1. Okay. So that's just about as simplified as we can get that expression. So we can go ahead and differentiate with respect to x. So this will be 1 over y dy over dx equals 2 over x plus 1 plus 1 over 2x squared minus 3 minus 1 over 2x squared plus 2. Okay, and then what we're going to do is, let me just see if I've done this correctly. Oh, I did, sorry. There is one, yes, okay. Sorry, there's one little mistake here, so I'm just going to erase this and go over it again. So, sorry, just forgot to use the chain rule here. So, of course, 2x squared, the derivative of that is 4x minus, and then use the chain rule here as well, so 1 half, oh, no, that was right. Sorry. Okay, here we go. So, yes, all right. Got a bit ahead of myself there. So we're going to take this 1 over 2x squared minus 3 times 4x, just doing that chain rule, and then minus 1 half times 1 over x squared plus 1 times 2x. Okay, that looks better. Sorry about that. So to simplify, 1 over y, dy over dx equals 2 over x plus 1 plus 4x over 2x squared minus 3 minus x over x squared plus 1. Okay, that looks a bit better. So then we isolate for dy over dx. So dy over dx equals y times all of that. So 2 over x plus 1 plus 4x over 2x squared minus 3 minus x over x squared plus 1. And then we replace y. So dy over dx x equals, and originally y was equal to all of that. So x plus 1 all squared times 2x squared minus 3 over square root x squared plus 1. So then we can just write that in. So x plus 1 squared 2x squared minus 3 over root x squared plus 1 all times 2 over x plus 1 plus 4x over 2x squared minus 3 minus x over x squared plus 1. And that is our final answer. Sorry about the confusion up there. I lost track a little bit. And thank you again to Loom and Google Keep and to my professors. And I hope to see you again in the next video.